Hi, I'm Luke Johnson of South Mecklenburg High School. Today we're going to be doing a crash course chemistry in chemical bonding, alright? First thing we have to ask is, what is a bond? Well, a bond is what holds atoms together to form molecules. For instance, if you take a molecule like water, H2O, chemical bonding is what holds the hydrogen and the oxygens together, alright? There are three main types of chemical bonds: ionic bonds, metallic bonds, and covalent bonds. And I'll be going through each of these to get today, as well as specific covalent bonds later on. Our first type of bond is an ionic bond, alright? Key word there is ion, alright? An ion is when an atom has more or less electrons than its neutral self does, okay? So an ionic bond is going to be a bond between a metal and a non-metal, alright? It's going to be a transfer of electrons as both of them try to satisfy their octets. So let's take a look at a molecule like sodium chloride, as you guys would know as salt, NaCl. In order to fill its octet, chlorine will actually take an electron from the sodium ion, making it an anion, and the sodium will lose an electron, making it a cation. Now these molecules, atoms, will want to come together to form NaCl, so then they both satisfy their octet rules and are now happy with the number of electrons they have. This is called a transfer of electrons. The electrons that they both need or don't need is what keeps them together. The second and easiest bond to remember is the metallic bond. You need to remember one word: metal. Alright? Metallic bonds are what happens between atoms that are both metal. Alright? That's all you need to remember. Now, metallic bonds, rather than transferring them like ionic, they share them, alright? And electrons are kind of passed throughout the entire structure, alright? So if you have a block of iron, these electrons are getting put all the way around. That's why electrical currents are able to flow through them so easily, because these electrons are already moving around through each of the atoms. Our last bond is the covalent bond, alright? Well, we had ionic, which is a non-metal and a metal, a metallic, which is a metal-metal. Covalent will be a non-metal and a non-metal. This is your water, this is your carbon dioxide, this is your xenon tetrafluoride. So important to remember here is that we have co together and valent. Think of valence electrons, alright? In a way, these valence shells of these atoms are together, alright? So they basically share their electrons in order to satisfy their octet rule, alright? They have a collective between the two, and they join them together in order to form things like carbon dioxide and water, alright? So remember, recap: ionic is a non-metal plus a metal, metallic is a metal plus a metal, and covalent is a non-metal plus a non-metal. That's all you need to know. So what we just looked at were intermolecular forces, right? Those are the bonds that hold atoms together. But what holds the molecules together? That would be the intermolecular forces, okay? Now, for ionic and metallic, if you have intermolecular forces that are ionic or metallic, the intermolecular forces are going to be ionic and metallic also, okay? Sodium chloride held together by ionic forces. A bronze alloy of tin and copper would be metallic intermolecular forces. But covalent is where it gets a little tricky as we break down into different levels, and we'll get to that in just a second. So now that we know what a dipole is, okay, let's look at a dipole intermolecular force, right? It's exactly what it sounds like. It's a dipole with another dipole, okay? So again, water. Notice how there's a temporary dipole where oxygen would be a partially negative and hydrogen would be the partially positive. So when you have another molecule, water molecule, looking exactly like this, this H plus partially, alright, is going to want to be attracted to this O minus, okay? And this is going to create a temporary bond between the two, making an intermolecular force, okay? Now the change in electronegativity of these two is so strong that it makes a strong intermolecular force. And that's when we have certain hydrogen bonding, okay? This is when hydrogen is with four certain elements, alright? That's going to be, remember, FONS. F-O-N-S. Alright, that's fluorine, oxygen, nitrogen, and sulfur, okay? The difference in electronegativity between hydrogen and these four atoms is so strong that when you have these partially positive and partially negatives, those intermolecular forces are going to be incredibly strong as well, okay? So remember, just think, dipole, dipole. If there's a dipole, it'll be attracted to other dipoles. And hydrogen bonding is when hydrogen is with one of these four elements. So now we go on to ion dipole. Again, we're going to use water, okay? Because water is one of the best examples of a dipole of a molecule. So again, H has a partial positive and oxygen has a partially negative, okay? The ion dipole, so let's just say that you drop sodium chloride into a solution of water, okay? And now now this breaks up, okay? It's called ionizing when it breaks up into its ions. We have sodium plus and chlorine minuses, okay? Now in solution. Now, remember, opposites attract. So this sodium plus is going to be attracted to this partially negative oxygen, okay? And now that's why it would dissolve in solution. When you put salt water, it dissolves in solution because of the molecular forces, as well as the chlorine minus being attracted to this partially positive H plus. And therefore, they're going to get together, and that's going to be another intermolecular force, okay? Lastly, we have van der Waals. Van der Waals is when you have a nonpolar, which means that there is no dipole, one of those molecules. How do they attract to each other? So we have, let's just take a bromine molecule, right? Bromine is diatomic, which means that it's Br2 in its natural element form, okay? So now it has an equal pull of both electrons on either side. So there isn't ever a dipole, or at least not a permanent one. We like to call this a temporary dipole, okay? Van der Waals. So think about how electrons aren't just going to stay still. They're charged, so they're moving back and forth between the two. So sometimes they're going to have a dipole going this way, sometimes they're going to have a dipole going this way. But point is, when you have another bromine molecule, all right, floating off in the distance, all right, having the same transfer of electrons going back and forth, partially positive, partially negative, between the two, all right, these are going to maybe form like a small, very quick interaction, all right, that will make them one. All right, but this is why this is incredibly, incredibly weak. Because think about how quickly these electrons are moving. That bond will be broken very, very, very quickly, okay? So that was another thing that's important, is that the ranking of these bonds, okay? Van der Waals is by far the weakest. You also see this as London dispersion forces, all right? That's important to note. Sometimes the exam might put that as those, but these are the exact same thing, London dispersion and Van der Waals, okay? Then the ion dipole would be the second weakest, followed by the strongest, which would be hydrogen bonding and or dipole, all right? Hydrogen bonding will usually be what's asked on the test because it's very easy to see with the fonts, but that is your basic rundown of your intermolecular forces. I'm Luke Johnson. Have a nice day.